Today we'll be looking into transformers. No, not that transformer, this transformer. It's the architecture behind the biggest large language models today. OpenAI's ChatGPT, Anthropic's Claude, Meta's Llama, and more. We'll be using the model from the 2017 paper, Attention is All You Need. The paper that reshaped how we build AI and helped spark today's rapid progress. I'll walk you through a concrete step-by-step example, translating an English sentence into French. First, let's do a quick overview so you know what we're getting into. We'll keep it simple for now and go into more detail later. We begin with the inputs. The inputs go through what I'll call the input processing layer. Here, each word is first converted into a vector representation, or in other words, an embedding. Then we add positional encodings to each vector. This is so the model knows the order of the words. Each of these resulting vectors now flows upward into what's known as the encoder. The encoder is made up of two main sublayers and can be repeated multiple times. That number is denoted as n in the diagram. You can think of the encoder as the part that reads the English sentence and captures its context and meaning for the decoder to use later when generating the translation. The first sublayer is the multi-head self-attention mechanism. This layer helps the model understand relationships and context between all the words in the input. It's basically how each word relates to every other word. It's called multi-head because this self-attention process is happening several times in parallel, each head focusing on different aspects of the relationships between words. Then comes an add and norm step. This adds the original input back to the attention output and normalizes it to keep training stable. The second sublayer is the feed-forward network, a small two-layer neural network applied to each position independently, followed again by another add and norm step. Now we move on to the decoder, which also consists of n layers. You can think of this as the part that generates the French translation one word at a time. Each decoder layer has three sublayers. First, the mass self-attention layer, which helps predict the next French word while only looking at previously generated words, not future ones. This restriction is what allows it to generate words sequentially. This might be a little unclear now, but will be better visualized once we walk through our example. This is followed by an add and norm step. Second, the encoder-decoder attention, or cross-attention layer, takes the encoder's output as context to help the model decide which parts of the English sentence are most relevant for predicting the next French word, followed again by another add and norm step. Finally, a feed forward layer. Just like in a decoder, this refines the output. And once more, we finish with an add and norm step. After the full stack of decoder layers has processed the information, the final vector is passed to two last layers. First, a linear layer acts like a giant dictionary, producing a raw score for every possible word in the vocabulary. Next, a softmax layer then converts these scores into probabilities, and the word with the highest probability is chosen as the final output for that step. This newly generated word is then added to the sequence of outputs that are fed back into the decoder for the next word generation step. Both the encoder and the decoder stacks are repeated n times, and for simplicity, they share the same number of layers. Now, let's take a look at our example. We're going to trace how our transformer model would process translating the English sentence, "The cat sat on the mat," to produce the French translation.
Le chat s'est assis sur le tapis.
The input processing stage has two parts, embeddings and positional encodings. First, we'll see how each word becomes a vector, then we'll look at how each position is added to it. Step 1. Input embeddings. The 6 words enter at the bottom as inputs. Each word is then converted into a numerical vector, a list of numbers that represent its meaning. Step 2. Positional encoding. Because the model processes all words at once, it needs to be told their order. A position vector is created for each word's position and later added to its embedding vector. The result is a set of vectors that each contain both the word's meaning and its position. Next, we'll take these new vectors and input them into the encoder's first sublayer, the multi-head self-attention mechanism. The goal of this layer is to let the model understand how each word relates to every other word in the same sentence. The cat sat on the mat. For example, when the model looks at the word cat, it should realize that sat is the verb that it connects to, and the is its article, mat is the object, and so on. To make this work, the model creates 3 different vectors for each word by multiplying the word embedding by 3 separate learned matrices. First, the query, what it's looking for. Next, the key, what it has to offer. And finally, the value, the information it contains. Now, let's focus specifically on the word cat. We take cat's query, what it's looking for, and compare it to the keys of all the words, including itself. Think of it like checking each key to see which one matches to what our query is looking for. we're essentially asking how much should cat pay attention to the words in the sentence. This comparison is done using a dot product, which measures how similar two vectors are, or in other words, how strongly they relate. After doing the dot product, we get a set of raw attention scores. These raw attention scores are then normalized using the softmax function, turning them into probabilities that sum to 1. This means cat mostly focuses on itself and on the word sat, since they're most relevant in context. Next, we use those attention weights to create a new version of the cat vector by taking a weighted sum of all the value vectors. So now cat becomes a blend of its own meaning plus information from related words, mostly sat. This process repeats for each word: the, sat, on, mat, and so on. Each word builds its own context-aware representation based on how it relates to others. After self-attention, every word embedding now carries information about the entire sentence. So, the original cat vector just meant cat. Now, the new cat vector represents the cat that sat on the mat. That's what self-attention does. Each word looks around, figures out who matters the most, and updates itself using that information. This example only showed one attention head, but language is complex. One head alone can't capture all relationships. Each head learns to focus on different aspects, like grammar, position, or meaning. So the multi-head attention layer runs several self-attention operations in parallel, each with its own learned parameters, giving the model multiple attention lenses. The outputs from all heads are then concatenated and linearly transformed to form a richer combined understanding before moving on to the next layer. Next, we move on to the first add and norm step of the encoder layer. You can think of it as a two-part safety check that keeps the model balanced. Here's what happens. The model adds the original input of the attention layer, say the original cat vector, back to the attention's output. The updated cat now knows that it sat on something. So it's combining both the original meaning of cat and its new contextual understanding. This addition acts like a shortcut that prevents the model from losing information as it goes deeper. It's a way of saying, keep what you already know, but add what you've just learned. After adding the two vectors, we then normalize the result. This step keeps all the values in a consistent range, like making sure no word signal is too loud or too quiet. It stabilizes training and helps the model learn faster and more reliably. Once every word has been updated with context and stabilized, the model gives each one a moment to process that new information on its own. That's what the feed-forward network does. Each word goes through the same small neural network independently. First, it expands the information, giving the word more room to think, like zooming in on the details. Second, it applies the nonlinear twist so it can form new kinds of relationships. Finally, it compresses everything back down, keeping only the refined meaning. In our example, the model might take cat, which already knows it sat on the mat, and refine that representation further, sharpening how it relates to the, sat, on, and mat before passing it onward. Just like before, the output from the feed-forward network is added back to its input, and the result is normalized again. Now, if you look back at the diagram, you'll see an NX next to the encoder block. That means everything we just went through, multi-head attention, add a norm, feed forward, add a norm again, isn't done once, but repeated several times. By the time we reach the top, every word's vector now fully captures the meaning of the whole sentence, ready to be passed on to the decoder. Now onto the decoder side. The decoder is going to generate the French sentence one word at a time, using the encoder's output as context. Think of the decoder as a student writing an answer while glancing at the encoder's notes. After each word, it passes through all its layers again, meaning each generated word is a result of a full loop through every decoder sublayer. So when we say turn 1, turn 2, or turn 3, each one represents a complete pass through the decoder to predict the next word. Before entering the first decoder sublayer, we begin with the output's input. At the very start, the only thing fed in is a special start token. This token is converted into a vector, made up of an output embedding and a positional encoding. No words have been generated as of yet. Now, this vector enters the decoder's first sublayer, masked multi-head attention. The decoder now asks, based on what I've written so far, what should I write next? Masked means it can only look at previously generated words, not future ones. For example, in turn 1, the start token only attends to itself. In turn 2, the start token plus
le,
can attend to the start token and
le,
in turn 3, start token plus
le,
plus
chat,
can attend to all previous tokens. Since turns 1 and 2 are quite abstract and harder to visualize, we'll begin our example at turn 3, where the decoder is now trying to generate.
chat,
This decoder sublayer creates query, key, and value vectors, but this time they all come from the decoder's own past outputs. For our current turn, generating,
chat,
the query is what the word should be next. The key comes from the previously generated words, like start, and
le,
value is the actual information content from those words. So this masked attention layer says, given what I've written so far, what should I write next that would make grammatical sense? So let's take a look at each token. The start token just indicates where the sentence begins. The next token is an article referring to a noun. So with this information, it can logically be deduced since
le,
is introducing a noun, the next likely token will be a noun. Let's see how it derives this in more mathematical terms. So the current query for
chat,
asks, which of the previous words are most relevant for deciding my next word? So it compares itself, in other words, dot product, with their keys. Then it turns those similarities into probabilities, softmax. So based on these probabilities, the masked attention layer decides I should pay most attention to
le,
because articles usually precede nouns. The decoder now collects the values, the meanings of the start token
le,
and mixes them together. This creates a summary vector, a kind of mental snapshot of what it knows so far. That summary roughly means the sentence has started and I just use an article,
le,
probably a noun comes next. This is the information that will get passed up to the next layer, the encoder-decoder layer, and we will use that to predict.
chat,
The model doesn't rely on just one perspective. It has multiple heads doing the same process in parallel. Each one might focus on a different kind of relationship, such as one head might focus on grammar, another on semantics, another on sentence position. When all those heads are combined, the decoder gets a richer sense of context. All of them together will make the
chat,
prediction more confident and accurate. Finally, the output from this attention layer goes through the residual connection, which adds the original input back in and keeps context from being lost, as well as normalization, which stabilizes values for the next layer. This helps prevent the model from forgetting what it already knew before attention. Now we move on to the next layer. We will refer to this layer as the encoder-decoder attention layer. Think of this layer like a student, the decoder, who's writing a translation and constantly flipping through their English notes. In our case, the encoder's outputs, to find what matches their writing. This layer uses the previous layer output in conjunction with the encoder's English context map to generate a word. When the decoder is writing a French word, it doesn't just guess blindly. It's essentially asking which English words are most helpful right now for deciding the next French word. To figure that out, it uses the query, key, and value vectors. Remember that the encoder has already produced a list of vectors, one for each English word. These are the encoder outputs, the notes about the English sentence. The decoder's current internal state is the vector representing which was just processed by the masked attention layer. This vector now implies that a noun is the logical next word. The encoder-decoder layer transforms the state vector into a query to find out which English word to focus on next. Think of a query like a question. Okay, encoder, my last layer told me the next word should be a noun. Point me to the most relevant information in your notes for finding it. Each query represents what the decoder is currently focused on. It's the question that the decoder is asking. Next, the encoder's output vectors, the notes about each English word, get split into keys and values. Remember, keys are like labels or tags that describe what each word is about, and values are the actual information or content about that word. Here's an example of the encoder's keys and values. Now, the query from the decoder gets compared to each key from the encoder. We calculate similarity scores. In our case, we're basically asking, I know I'm looking for a noun. How relevant is each English word to what I'm trying to find? These scores are, again, just like in our encoder layer, found using a dot product between query and each key. Then we apply a softmax to turn these into probabilities. Now, the decoder combines the values using those weights, giving more attention to cat and less to others. This gives a context vector, a blended representation that highlights the most relevant English meanings for the word that we're trying to generate. But remember, they're not just one set of queries, keys, and values. There are multiple heads. Each head learns to focus on different relationships. All heads' results are then combined and fed forward for richer understanding. So far, we have a context-rich vector that has just been produced by the encoder-decoder attention layer. This vector has combined the decoder's own progress with the most relevant information from the original English sentence. Now, this vector is passed to the feed-forward network. Think of it as the final thinking or digestion step within the layer. The attention layers were all about gathering and compiling information. The feed-forward network's job is to process this compiled information more deeply, looking for more complex patterns and relationships, making it even richer and more useful for the final prediction. After this, it goes through one last add and norm step, just like the other sublayers, to ensure stability. The output is now the final, most refined vector for this turn. It represents the decoder's best possible understanding before it makes its final decision. This vector is then passed up to the next decoder layer in the stack, where this entire process, masked attention, encoder-decoder attention, feed-forward, repeats. After the vector has passed through the entire stack of decoder layers, the NX part, it arrives at the final two layers that sit on top of the entire architecture. This is where the decision is made. The linear layer acts like a giant dictionary containing every single possible French word the model knows, tens of thousands of them. It takes our final, highly refined vector from the top of the decoder stack and projects it into a massive list of raw scores. There is one score for every single word in the dictionary. Based on the context vector, which strongly suggests a singular masculine animal, the scores might look something like this. The softmax layer takes this huge list of raw scores and does something very simple and elegant. It turns them into clean probabilities that all add up to 100%. The word with the highest probability,
Chat.
is selected as the output for this turn. The entire process now begins again for turn 4. The decoder's input becomes start token,
Le chat.
and it will loop through all the layers to predict the next word,
C'est.
until it eventually predicts a special end token to finish the sentence. And there you have it. That's the entire journey, from an English sentence being understood by the encoder to the decoder writing the French translation one word at a time. It's a clever dance between all those layers, but it all comes down to that magic of self-attention, letting the model figure out what's important. This very architecture is the engine inside the tools like ChatGPT that are changing our world. If this deep dive helped clear things up for you, do me a huge favor, smash that like button. Be sure to subscribe so you don't miss the next one, and drop a comment below letting me know what other AI concepts you want to see broken down. Thanks for watching, and we'll see you in the next video.